Hi everybody, and welcome to lesson 2 in electromagnetism. Today's lesson is all about electromagnetic induction. So first of all, what is the meaning of electromagnetic induction? The word to induce means to make happen. So electromagnetic induction is all about changing energy from one form to the other. So how can we produce electrical energy? And one way to produce electrical energy is to be able to change mechanical energy, energy of movement, to electrical energy. And how is this possible? Now this is possible if you have three things. So what you need is a coil of wire, because it's in a conductor you need charges to flow. Okay, and then you also need a magnet, because around a magnet there's a magnetic field. Now you put the two together, but if the magnet is not moving and neither is the coil of wire moving, nothing's going to happen. So the third thing that you need is either the coil moving relative to the magnet or the magnet moving relative to the coil. So if you have a magnet moving in and out of a coil of wire, what happens is you will get an induced voltage, okay? And why do we have an induced voltage? The reason why this happens is when there's a changing magnetic field. Now, the word that we use for changing magnetic field in year 13 is when there is changing flux. Remember, in the first lesson, we learned that the magnetic field is also referred to as flux, and the magnetic field strength is referred to as flux density. That's the amount of field lines in a particular area. So whenever there's relative motion between a magnet, because it has around it the lines of flux, those lines are not really there. It's just for our convenience we talk about lines of flux. Okay, there will be an induced voltage, and the reason why there's an induced voltage is because the electrons in the wire feel a force, and the sort of force they feel is a magnetic force, because there's a magnet close by, and this magnetic force causes the electrons to move. And when you have electrons moving, there is charge separation, and this charge separation results in an induced voltage. Okay, and the size of this induced voltage depends on a few things. It depends how quickly the magnet's moving or the wire is moving. So how quickly is speed? Then it depends on how strong the magnet is. So that is flux density or magnetic field strength. And then the other thing that all this depends on is the length of wire. So the size of the induced voltage is actually equal to V equals BVL, where V is the size of the induced voltage. So I've kind of gone through all this. Okay, now we're going to look at what happens if you just have a straight wire in and moving in a magnetic field. So a magnetic field can act in any one of 6 directions. So it can act to the left, to the right, up the page, down the page, into the page, or out of the page. Now, just for convenience, let me just have the magnetic field going into the page, and that is represented by crosses. Okay, so if you have a conducting wire that is moving in the magnetic field, the electrons in this wire, they're going to feel a force and they're going to move. Now, we don't know which way they're going to move, and in order to know the direction of movement of the electrons and therefore which end becomes positive, there are lots and lots of rules, but the rule that I use for electromagnetic induction is the left-hand slap rule. So in the left-hand slap rule, the lots of lines indicate the magnetic field lines. The palm of your hand is the direction in which the rod is moving, and the thumb indicates the direction of the current. It indicates the direction of the positive end. Okay, so current is the direction in which a positive charge will move. So let us just look at this. So let's just look at this one. So you have a rod, and I pointed my fingers into the whiteboard because the field lines are going into the page, and the palm of my hand is moving this way. My thumb is pointing upwards. Now, because my thumb is pointing upwards, the top end of the rod is going to get positive, leaving the bottom end negative. So what actually happens is all the electrons flow down. Now, as the rod keeps moving, more and more electrons keep flowing down. But this doesn't happen indefinitely. Now, what's actually happened is because of this charge separation, when charges are separated, you've got one end of the rod positive and the other end negative, there's going to be an electric field. Now, the electric field is going to exert an electric force on the electron, and that's in the opposite way. So the magnetic force causes the electrons to come down because the rod is moving, but the electric force is trying to pull the electrons up the other way. So this charge separation continues till both the magnetic force is equal to the electric force. Okay, this is something we did last year, but I'm just going through it again. All right, and the size of the induced voltage here is again given by the same formula, V equals BVL. Okay, now if instead of a straight wire, let's say we've got a coil of wire and you're just moving the coil through a magnetic field. So I'm just going to draw 3 different positions of the coil. So this is position 1, position 2, and then I'll just squeeze this last one over here. Okay, so let's say you've got a coil of wire, and we just call that ABCD, some sort of name, and it's moving in this direction, A, B, C, D. So this one is a coil that's entering a magnetic field. In the second one, the coil is totally in the magnetic field. Okay, still moving in that direction, but all of it is in the magnetic field. And in the last one, the coil is leaving the magnetic field. So part of the coil is actually outside. I'm not going to write on this thing some sort of a label there. That's B, C, D. So it's still moving that way. So let's use our newly learned left-hand slap rule to find out what is the direction of the current. So the slap rule is used to find the direction of the current when it's quite straightforward. Okay, so the coil is moving this way and there's only a voltage induced along BC. And can you see my thumb is pointing upwards? So the electrons along BC are feeling a push force upwards, and because this is a complete loop, you're going to have an anti-clockwise current. Okay, now the size of the voltage induced is B equals BVL, but the size of your current depends on the induced voltage and the resistance of the wire. Okay, what happens in C? In C, there's an induced voltage across in this number 2, there's an induced voltage across this end, BC, as well as an induced voltage across AD. They're both in the same direction because all the electrons are feeling a force upwards. Because they're in opposite directions, you end up with no current. They cancel each other. Okay, and then in the last one where it's leaving, there's no induced voltage in this part of the coil because it's outside the magnetic field. However, there is an induced voltage across AD, and so the electrons feel a force and the current is going to go in this way. You're going to end up with a clockwise current. So you see the current is anti-clockwise while it's entering. There's no voltage induced while it's totally in the field because they're in opposite directions across AD and BC. So they cancel each other. And when the coil is leaving the field, the current is in the opposite direction. It's a clockwise current. Okay, now just one more thing for this lesson is why is there no current induced across AB and DC? And then in order to understand this, I'm just going to draw like a really fat wire so you can see what's actually happening to the electrons inside the wire. Okay, so there's your wire, and there are all these electrons that are free to move, and they will only move when they feel a force. And the magnetic field is still into the page, and the coil is moving that way, right? Okay, so I'll just draw. That's your magnetic field, and the whole coil is moving this way. Okay, this is A, B, C, D. All right, so when it's moving that way, the coils along the electrons along AD, the electrons, no matter where they are, they're all going to feel a force in this upward direction. Okay? The electrons along AB, they feel a force in the upward direction, and they're pushed along the wire, and they kind of end up pushing everything else. Okay, the electrons over here also feel an upward force, but that is against the edges of the wire. It's what we call across the wire. So they're not going to, they're just kind of getting jostled against the walls. So they're not, that is why they're not responsible for the electron flow. They're kind of just going against. So there's a word along the wire, and this is across the wire, going from one end to the, the edges of the wire. So that's why there's no voltage induced across AB and DC. And I hope that made sense. And I'll make another video showing you how to do questions on calculating the induced voltage in a straight conductor. It's just revision from last year, so it should be fairly straightforward. Bye for now.